Okay.
Everybody, our speaker today is Luca Cafaro from our institute. So he is PhD student. He was PhD student of you, right? But now he's
soon to be yours.
and the topic of his talk will be about the collapse in effective quantum gravity, and it's the joint work with Lorenzo Cipriani, Francesco Fazzilli, Fasci Soltani. Fasci Soltani is also postdoc in our faculty. So
okay, thank you. So thank you for the introduction. Okay, so as you said, this is a joint work that is now on arXiv. It appeared on the 24th, I think, of Christmas. And what I really want to do now is give you more or less an overview on the topic. So we're going to deal with spherically symmetric stellar collapse in this effective theory rooted in loop quantum gravity. And I will start from the easiest case, which is a star made of pressureless dust. And then eventually I'm going to end my talk talking about pressure, which is what this print is dealing with. Okay, so let me start by giving you a couple of motivation on why this is done. So in general, and this transcends loop quantum gravity, the reason why people add quantum correction to classical GR is, among the many reasons, to solve the singularity. But assuming that the singularity is resolved, then this raises another question, which is, what is the fate of the black hole? So what happens to the matter if it is not crushed into the singularity? And those are the answers I want to provide an answer for. Okay, I will just state the framework of this theory. So starting from classical GR, what is usually done in these models is to start from this metric, which is the line element of a spherically symmetric spacetime, written in terms of this n and nr, which are respectively the lapse, and the r component, the radial component of the shift vector. The other two components are zero by symmetry. And these other e's here, those are functions that are related to the densitized triads here. So we define this A and B in the following way, and we also have their conjugated variables that are related to extrinsic curvature in this way. We're going to use this later. Okay, this is step 0. Step 1 will be to impose a certain gauge, which is called the aerial gauge. So we just choose this function to be the square of the physical radius, this r, and then it is convenient. It is not necessary, but it is convenient to redefine this EB in terms of a new function epsilon, which is a function of t and r in general. And the reason why is that if we do so, then we get to this metric, which is well known in classical GR. This is the so-called Painlevé-Goulstrand gauge, or PG for short. As far as I know, originally the PG gauge was with epsilon equal to 0 and n equal to 1. So that's why people started fully generalized PG gauge, but that's just a matter of the name. Okay, I told you that this is semiclassical work. So let's add some semiclassical ingredient to the classical picture. I'm not going into details because I don't think I have the time, but maybe we can discuss this later if you're interested. So what this semiclassical theory does is modify this r component of the shift vector and this h, which is the so-called Hamiltonian constraint, with this hm taking care of all the matter part. So here I'm not specifying any property of the fluid. And you see the presence of this delta is what gives you the semiclassical setting. This is the smallest non-zero eigenvalue of the area operator of L2G. And broadly speaking, this is the square of the Planck length. So it's very, very tiny. And the classical limit is recovered sending delta to 0. So you see you get sine function. So this is of the form sine x over x for x going to 0. So it's easy to take the limit that you can check on any textbook. If you take this limit, then you recover the classical case. Okay, good. So this is the starting point. We can, from here, recover what is called a physical Hamiltonian, H. And with this physical Hamiltonian, we can take the Poisson brackets and compute the equation of motions, which are this is the Hamilton equation equivalent of the Einstein's equations. So from here, you know all the dynamics. For conveniences, we will just rewrite them in terms of this new function, epsilon. and in terms of the gravitational mass, which is related to being this way. It's quite complicated, but you can do that. And actually, it's much easier to work with these two variables. I didn't write explicitly the equation of motion because they're pretty complicated. And what people realized is that working with this PG gauge is maybe too complicated. So it is better to change coordinates into this so-called Lemaitre Bond gauge, which we'll call LTB for short. Here I stressed the main differences. So you see the time variable is the same, and you can think of this T. So the average surfaces of T equal constant are orthogonal to the flow of the fluid, or if you want this for velocity, is proportional to dt. In the dust, this will be the co-moving time. However, the radial coordinates are different. So here, this lowercase r, I will refer to this one as the physical radius, and that's what gives you the proper area by multiplying by 4 pi. But on the other hand, here we have this capital R, which is the so-called co-moving radius. And the metric here is diagonal. So this is the explicit change of coordinate. And you see here the partial derivative of the physical radius with respect to t, which if you want is the velocity of the fluid, is given by the R component of the sheet vector. Okay, so that's the semiclassical setting. What we could do now is just rewrite the equation of motion in this new gauge, in the LTB gauge. And that's what I'm going to do. I will start, though, starting with the dust.
Question.
Sure.
So what is this co-moving?
So this is, so if you think of dust, which is the easiest case, and you can peel the star, okay, the spherically symmetric star, into all different radii. So you can think of thin shells labeled by this radius. So a particle of dust that starts on the radius stay at the same radius. So it's co-moving with the collapse, okay? That clear? So yeah, so you can use this R to label the shells. So each shell has its own co-moving radius, meaning if you see it there, then you won't change your radius. Not this co-moving radius, but clearly this one will change in time, the physical radius. So in the sense, it's co-moving. Okay, so let's start with dust. This is the easiest case one can think of. And in the LTB gauge, the stress energy momentum tensor is very easy. You get just one non-zero component, which is the energy density rho. And if we have no pressure, each particle of the fluid follows a geodesic. This means that we can write the forward velocity as dt, or equivalently, we can set n equal to 1, or any positive constant that can be reabsorbed in t. So this is the starting point. We can write down the equation of motion, which are relatively easy. You see, both m dot and epsilon dot in this gauge are 0. So the mass of, so if we think this mass as a function of t and the co-moving radius r, the mass contained inside a shell labeled by co-moving radius r is conserved. It means that there are no fluxes going around. And this epsilon has a very precise physical meaning. You can guess the physical meaning from here. So in the classical case, when delta goes to 0, or if you want take this r to be big enough, so we're far from the Planckian region, you get just this first bracket contribution. You divide by 2, here you get the Newtonian kinetic energy. You bring this piece on the other side, and this becomes the Newtonian potential energy, which means that epsilon divided by 2 is the Newtonian mechanical energy, which is conserved. So if epsilon equal to 0, it means that all the shells start at infinity at rest. If it is positive, they start with a kinetic energy, initial kinetic energy. And if it is negative, it means that the star is allowed to start from a finite radius with 0 kinetic energy. So this divides, broadly speaking, this scenario in 3 cases, which are called the bound, when epsilon is lower than 0, the marginally bound, when epsilon is 0, and the unbound, when epsilon is bigger than 0. Okay, so what we could do now is just choose a density profile, which is our initial condition, and get this function m, which is constant in time. Again, start from the easiest case, which is the so-called Oppenheimer-Schneider model. And I think this was realized in the 30s originally. So inside the star, we have constant energy density, and then in the vacuum is 0. So you get a sharp discontinuity, a jump discontinuity. it does not matter because if there is no pressure, it's okay, it's matchable. With pressure, you cannot do something like this, but with dots, you can. We integrate the equation for r dot, and that's what we get. So here there's r, and on the y-axis, there's t. Each of these colored line is one shell labeled by one moving radius, r. And you see, so the star is collapsing. So here, these shells are focusing, and in classical GR, they will be crushed inside a singularity, which is also called shell focusing singularity, because you can think of this shell focusing to a singular point. However, we introduce quantum correction, which means that here we get a repulsion, and these shells, they re-expand after hitting this bouncing radius, this turning point. Now, this picture itself is for epsilon equal to 0. You can show that qualitatively, epsilon positive is more or less the same. And if epsilon is negative, instead, you have a recollapse at a certain point. So this expands up to a certain point, and you have a second turning point here, and then there's a recollapse. They will reheat another bouncing point and go on and on. So you get something like a cyclic collapse. And since I'm talking about this, let me mention the work that Professor Lewandowski had done in this context. So within his collaborators, he derived the maximal extension of this kind of space-time. So you can check that the vacuum admits in Schwarzschild coordinate a nice modification of the Schwarzschild metric. So if delta goes to 0, this is Schwarzschild. You get delta corrections. So originally their work was with epsilon equal to 0, but it doesn't change much if epsilon is not 0. By the way, epsilon 0 is a constant. This is the value of epsilon at the boundary of the star, which remains constant throughout the vacuum. You see here, just a couple of words, this is quite equivalent to the resonance from black hole, except here instead of the singularity, we get this reflection surface. So if we track one of the particle that follows a geodesic, then it enters B, which is a trapped region. Eventually, it will come here to C, which is non-trapped, bounce in this point, enter an anti-trapped region, and get to square plus. Or if epsilon is negative, once it gets here, it recollapses again, and you get something cyclic. It is actually analogous to the closed cosmology. When you get k equal to 1, you get, once the universe expands to a certain point, then it recollapses. And if you allow it to bounce, then it goes on and on infinitely many times. Okay, this was the easiest case, really the easiest. What happens if we generalize this one a little? So we don't have a star with homogeneous dust in the inside, but we get two profiles. Broadly speaking, there is a difference if we consider the so-called one-tail profile or two-tail profile. So in other words, if we consider just one peak of this function, it can either be on the far left or in the middle. We do not consider the peak being on the far right because that would be equivalent to this one. Okay, so we integrate the equation of motion with these two profiles, and what we get is this. Okay, so this is very colorful, beautiful to look at. But the most important thing is that this is not symmetric anymore because the dust is no longer homogeneous inside the star. And if we magnify this picture, this is what we get. And we see there are points here where the shells, they cross. So those are called shell crossings. The reason why I divided the cases into one tail and two tails is because with one tail, this happens soon after the bounce. So you see here the shells are re-expanding, whereas here are still collapsing. So this shell crossing will also be present in classical GR because this happens before the bounce. This one instead would happen after the singularity, so those are not present in classical GR. Those are a pure quantum effect. Okay, shells cross, is that bad? Well, the answer is yes, but there is a way out. So when two shells cross, what is happening is that two different shells labeled by two different common radii, they share the same physical radius. So in that point, this transformation is no longer invertible. And you can check that the Jacobian of the transformation is actually 0. So if we go back to the definition of the gravitational mass and we recover rho from it, you see that these are prime, with prime be the derivative with respect to the common radius. This is in the denominator. So if it is 0, then it might happen that m prime 2 is equal to 0. In that case, rho it is allowed to be finite. If that happens, we talk about shell crossing. But in the general case, m prime is not 0. And also in the cases that I showed you before, m prime is different from 0, which means that you get shell crossing singularities. And those are real singularities. So scalars diverge at that point. Anyway, those are not like the Schwarzschild singularity. So those are called weak singularity because you can extend space-time past those points. It's quite complicated. It's very complicated, actually, from a practical point of view. What you must do, well, you first realize that if this happens, it simply means that the set of equation of motion in the coordinate, in the LTB coordinates has simply failed. It means you cannot recast the system of Einstein equation as partial differential equation. So you must recast your equation of motion in this form with any variable we want to study and look for what is called a weak solution. Now, if we go back to the PG coordinate, to the PG gauge, the equation of motion has precisely this form, rewritten in terms of epsilon and b rather than m, or if you want this beta, which is just a redefinition. And you can check that this beta is actually discontinuous at the location of the crossing, which I will denote by L. And this is why the system of partial differential equation fails, because it's no longer differentiable in that point. So we look for weak solution, which are a function that solves the integrated equation of this equation here, with phi being a test function, which is smooth enough and zero on the boundary of the integration domain. A little bit of math, and in our case, what we get is something like this. So we get that dl over dt is given by this complicated function, which is given by the difference of the two limits. And this is called the Rankine-Hugoniot condition, and it's well known in fluid dynamics. So what this is describing is a shock wave. In other words, when two shells cross, a shock wave is formed. And at that point, we get a divergence. And however, I told you that those are weak singularities because we can still track the dynamic of the shock through this Rankine-Hugoniot condition. But from a practical point of view, this is extremely complicated because these equations are so long and it's not easy to do without any approximation. So that's where 99% of the literature stops, and there's not much said about this. Also, in the classical case, that doesn't matter because if a shell crossing occurs, this shock then eventually will be crushed into the singularity. But if the model is not singular anymore, then this raises the question what happens to the shock. And as far as I know, this is still unanswered. There are some possibilities which I'm going to discuss maybe at the end, but this is still unanswered. Okay, and this concludes the case of dust. So let me introduce the work we have done. So starting from here, we can add pressure to the model. So instead of studying dust, we studied an isotropic fluid, which means that the stress energy tensor is this general form with pi being the radial component of the pressure and sigma the tangential or angular pressure, with two equations of state that must be chosen. We can write down the equation of motion, still in the LTB gauge. Those are much more complicated than the one in the dust. You see, R dot is practically the same except for this n, but m dot and epsilon dot are no longer zero. Also, another important thing to say is that n is no longer constant. So you get an equation for n, which comes from the conservation of this energy tensor. And as a consequence of the pressure is that the particle of fluid do not follow geodesics anymore. So you get an acceleration, which is just radial, as it should, which depends on n prime over n. Now, if we look at this n prime over n, you see that there are two terms. One is the gradient of the radial pressure. This gives us the usual force that's also present in ideal gases, for example. When you squeeze a balloon, there is a resistance, and this is given by the gradient of the pressure. But there's another term, which is given just by the anisotropies of the fluid. So you see, if we get a perfect fluid by imposing pi equal to sigma, then this term disappears. But if sigma is bigger than pi, we have an outward pointing force, or vice versa. If pi is bigger than sigma, it points outwards. This is an extra term. So this is pretty general. If you like numerical integration, you can just choose two equations of state and have fun integrating the system. What we did in our paper is just to show two easy cases because we don't want to get the general case, the most general case. What we wanted to do is to show that these crossing singularities appear also when pressure is present. So I will first present a model where pi is 0. So this is highly non-realistic. We just have angular pressure. And the reason why is because the equation of motion simplifies a lot with pi is equal to 0, and we can recover some analytic results. And the other result will be the perfect fluid, so where pi is equal to sigma, but that's entirely numerical. So we just flash some results and that would be it. Okay, let me start from here then. So we get this energy momentum tensor, which shows a linear equation of state, which is actually a very dumb choice, and I'm going to comment on this in a couple of seconds. The equation of motion are relatively easy, the mass is conserved, and the epsilon is not. Notice one thing. M and epsilon do not depend explicitly on rho. So if shell crossing occurs, they're not infinity, even at that point, which means that we can integrate this R dot even after a shell crossing has occurred. And this was the case of dust. But the problem is that it makes no physical relevance after a shell crossing singularity. I'm going to comment something more when I'm going to show you the results, so I'll stop here. Anyway, so let's go back. We have this equation of motion. We can choose a profile and then integrate. But before doing that, I want to show that we can solve analytically this n and this epsilon. These are the expressions, relatively complicated, especially the epsilon. So our n is just a constant, and the epsilon depends on this new parameter, which is k, and this is the initial, if you want, Newtonian kinetic energy of the shell. So they may start with some initial velocity. And to ensure the positivity of this square root, then this k must be lower than the inverse of this function, which I will label by kmax. This actually makes sense because loop quantum gravity is essentially UV finite. We get a minimal length. So it makes sense that we have an upper bound in the energy. And indeed, if delta goes to 0, this goes to infinity. So we get no upper bound to the kinetic energy in the classical cases, as it should. Now again, for simplicity's sake, we will just choose k, which is dictated by the initial condition, to be proportional to kmax, multiplied by this eta, which is a constant between 0 and 1. And this means that this entire bracket is just a constant. So this gives us a one-parameter family of epsilon, if you want, dictated by the initial conditions. Okay, the reason why I told you that this equation of state is very stupid is that because it does not satisfy what is called the regularity condition. So in order to have a regular star at the center, it must be that this pi here, this pi must be equal to sigma at the center. But this cannot be the case because pi here is identically 0, and this sigma is not 0 at the center because rho in general it is not, and omega is just a constant. What's the consequence of this? Well, a singularity. So all this model to remove the singularity, and now we get a singularity. It's not that bad because I'm going to show you that nothing can fall into this singularity in a semiclassical setting. But in general, you don't get this if you choose another equation of state. But the point is, if you choose another equation of state, then you can forget finding an analytic solution. So unfortunately, we have to. But again, this is not that bad. So this is the full expression of our dot. There is no way to solve this analytically, but we can still say something if we look separately at those two contributions. So if you want, this is the classical bracket, and this is the quantum corrected term. For example, we could look for turning points. So where this velocity is 0, and you can check that the acceleration changes sign in those points. So starting with the classical term, if we impose this term to be 0, it would be nice to recover a solution as r as a function of the comoving radius and omega. The expression is too complicated. This is not possible. So all we can say is that turning points, if happen, they happen for r bigger than 2m, which is obvious because if r was lower, it would be in the trapped region, and in the trapped region, it clearly cannot be 0. So this is telling something trivial. However, if you repeat the same argument for the quantum term, you get that here too, you must get a lower bound for r. So turning point can happen at r bigger than this function of the comoving radius, which is complicated. I'm not going to write it down, but you can show that this function is 0 only if r is equal to 0, which means that if you start, so if you pick a shell, okay, away from the center, labeled by a certain r, so this shell will collapse. It will bounce at a certain point without touching the 0, because it must be bigger than this function, which is not 0. So that's why I told you that nothing can actually touch the singularity. There's also another reason for it, but it is probably the strongest one. So nothing will be crushing the singularity, information will not be lost. And even if this model is singular, we can still study the overall feature of this star collapse. Okay, so I told you that it would be nice to find R as a function of omega. We cannot do that, but we can find omega as a function of R just by taking the logarithm of this function here. And this is what we get. It's a pretty ugly function with two asymptotes, one in 2m, one in R physical radius equal to co-moving radius. This dotted line is one chosen value of omega, because once we choose the equation of state with omega equal to constant, this is set. In this graph, I think is 0.4, if I remember correctly, but it's completely general. And clearly this is for one shell only. So we selected one moving radius, which labels one shell. Okay, why I'm showing you this picture? Okay, so if we start with physical radius being equal at the moving radius initial time, and this choice is always possible, it means that any other time, since the shell is collapsing, this physical radius will be lower. So we start at the chosen omega from physical radius equal moving radius here, and then we start moving on the left. And at a certain point, we will hit this curve. And once we do, basically we have found an R that solves this equation. So this red square bracket equal to 0, which means we have found a turning point. So the shells collapse, and at a certain point, it will turn around, so it will start expanding. Here, the velocity is 0. If we look this in this other perspective, so let's focus here on the left. This is the same graph where we more shell. You see, you get intersection for the innermost shells. So these two will have turning points, whereas the other shells here will not. This means that the core of the star will collapse for a while, then it will re-expand, whereas the boundary will collapse. And this means that shell crossing are unavoidable. So we will get at a certain point shell crossing. There is nothing we can do about it. If our chosen omega, so this dotted line was negative, and we started from here, there would be no turning point, because we move on the left and we'll never cross the curve. So no classical turning point can occur for negative omega. Whereas here, if we repeat the same argument for the quantum case, no matter what omega we choose, this will always intersect the curve, because this omega spans the whole real line. So there is always a quantum turning point. So the star bounces, and nothing is focused into a shell crossing singularity. In a shell focusing singularity. Let me just say one thing. Yes, I still have time. So if this chosen omega was negative, I told you we move on the left and we do not cross this curve. And this is true. So we move here on the left, but eventually we will hit this other curve and have a turning point in the quantum region, and the star will start to expand. But if it starts to expand, eventually the physical radius will be bigger than its initial value, which means that it can cross the right part of this curve, and here it will recollapse. So we get a cyclic dynamic for negative omega. I'm going to show what I'm seeing here also on after I'm going to take care of the numerical integration. So I think this concludes the analytical part. Now it's time to integrate. I will just show now a case where we don't have a center. So the star is hollow, so the density here is 0, then you have a peak at a certain point, and then it gets to 0 in the vacuum. If we do that, that's what we get. So for negative omega, you see we get a shell crossing after the bounce here, and you can see that all these shells recollapse at a certain point. It will be more clear in a minute. Anyway, I told you that the numerics do not know about the shell crossing singularity, so they keep going, but physically speaking, this makes no sense past this point, so past the first shell crossing. Because when that happened, then we must study the Rankine-Huguenot condition and see what happens to this shock. Okay, what about positive omega? That's what I told you. So the outer shell collapse, the inner wall collapse for a while, but then re-expands and then cross at a certain point, and you get this butterfly. That's what we called it. Okay, so if I introduce the center instead, so now we have a peak on the center, that's what happens. Qualitatively is similar, but the reason why I showed you that before is because here it's very complicated and it's quite messy, it's not easy to understand. What I can tell you is that all of these shell bounce back and forth between a classical and a quantum turning point, and you can check that this frequency increases as you get close to the center. But also, the amplitude goes to 0. So the actual center will not bounce, it will stay put in there. So the singular center is detached completely from the rest of the star, because it will stay at the same point, and the rest of the star will never touch that point. So nothing falls into the singularity. Here instead, it's quite similar. There's not much to say. So this falls, this re-expands, and they cross here. At the center, something peculiar happens, because you can realize that the classical turning point is actually lower than the quantum bouncing one. So you get still here a quantum static dynamic, but the frequency is much lower. So you get something more dull here. But okay, this was a highly unrealistic case. I mean, stars have radial pressure, clearly, but we got some analytic results. And we saw that in this model, shell crossing cannot be avoided. So let me turn now to the perfect fluid, again with a linear equation of state, but the equations are too complicated to be solved analytically. What I can tell you is that now both m and epsilon depend explicitly on rho through through p, right? So here this is omega rho, and here too we have rho. So when a shell crossing happens, we get infinities also in m and epsilon, which means that this equation will be ill-defined, and the computer stops once a shell crossing occurs. So if you look at some pictures, so that it is, it's a different layout. So the black lines are shells, and between two black lines there are, I think, 10 shells, something like this. The color is instead the density, logarithmic scale. When it gets black, it's where it's going to infinity. And exactly at this point, so in the top of this graph is where a shell crossing occurs, and the simulation must stop here, because you get infinities also in R, and yeah, you must stop. So here you get a shell crossing singularity, and here too. So these are 3 different pictures for 3 different profiles, but as you can see, they're qualitatively the same, and there's not much to say here. So it happens also in the perfect fluid, which is a highly more realistic case, which means it seems to be a general feature of the model. We cannot disregard this shell crossing. Let me just conclude by showing you a picture of the causal structure for yet another profile. Here the shell crossing happens, and if we focus in this region, so this is just a magnification of this portion, then you see you can study the zeros of the null expansion. You get a trapped region, a non-trapped region, and an anti-trapped region, and the shock is forming just in the boundary of this non-trapped with the anti-trapped region. So here a shock will form, and it will move outward, but it's not clear what happens, because here you still have a trapped region. There were some studies in the dust cases. What was shown from numerics is that these shocks move space-like. It can actually move outward also in the trapped region. This is most likely not physical, it's some artifact. So it's not really clear what happens. I know people are investigating this. Also in the dust, it's not clear, so there's not much to say in the presence of pressure. So that's our current understanding of the picture, of the whole picture here. Let me conclude just by saying that there are some static solutions if we study the vacuum. In Schwarzschild coordinate, we get a line element of this form, which is closely related to the one I showed you in the work of Professor Lewandowski, except now epsilon is not simply a constant anymore, but it is allowed to be a function, because in the vacuum we get this equation. So in the dust case, we get that n is equal to 1, or a constant anyway, so epsilon2 must be a constant. However, it seems that in more general setting, n can also be a function in the vacuum, which means that this epsilon in principle can be a function. It is not clear whether these solutions are physical or not. Maybe not. So maybe epsilon is forced to be a constant, but again, I don't really know the answer, so that's all I'm going to say. So this is a possibility of epsilon being a function here of the radius, but it might also be not physical. Okay, I will conclude just by stating what we know and what we don't know. So from this analysis, we got a set of effective equation of motions with this anisotropic fluid in spherical symmetry. It is quite general. So, I mean, if you like numerical simulation, you can just choose the equation of state you want, integrate it, see what happens. Okay, what we realized by studying these two models is that in general, if you choose the right equation of state, the singularity is resolved and you get bouncing star. On the other hand, we didn't solve the problem of crossing singularity. So it's not a problem per se, but you must study this shock wave. The dynamic of this shock wave is extremely complicated. And this is still unanswered. So what is the fate of the black hole? The answer is we don't know yet. Hopefully, I mean, people will in the next future, but at the moment, all we know is that once we shall cross, a shockwave is formed, something will happen. It will not be crushing the singularity, it will bounce, but then this is not clear. Okay, so that's all I wanted to say. I'll just review some references divided by arguments if you want to know more about this stuff. And I will conclude my talk here, and I'm open for questions if you have any.
Sure. I have a question. So I understood that so why people were happy with the resolution of singularity quantum gravity, because it was avoiding this like the ill-defined dynamics. Yes. So I understand that in your model you still have singularities. So is it?
Yes, with singularity, yeah. What we did avoid. Okay, so if you go back here. No. Okay, here. So these equational motions avoid the shell focus in singularity, which means, okay, maybe it's more clear. Okay, here in the Oppenheimer Schneider. So this star collapses, but I mean, the fate of this star will not end inside a singular point. So you don't get this strong singularity, okay? Because here it bounces. So at this scale, at the Planckian scale, gravity gets repulsive. Problem is, we do not avoid the singularity coming from the shell crossing. So when this happens, rho explodes because a shock wave is formed and you get a discontinuity. I mean, this is probably just an artifact of the fact that we are not considering many other, for example, we are not considering microscopic physics. So this happens also in fluid dynamics, but you know, you can smooth the front because something else is happening. And maybe what we could do here is consider also the macroscopic physics, and this will smooth the front of this shock wave and give you a finite rho in that point. If that happens, then this model will be singularity free. But as far as we know, this shell crossing singularity gives you singularities. But I mean, the space-time can be continued past this. So yeah, those are not strong singularities like the Schwarzschild one. Those are curable in a certain sense. But yeah, that's a huge impediment if you want to study the dynamics and the fate of the black hole and the Kirchhoff structure on the whole. But yeah, those are still toy models, so those are far from being realistic, clearly, that there is a lot to be done here, yeah. Also, it's not clear if the semiclassical approximation holds really close to the center, because maybe here some other quantum strong quantum effect will kick in and something else will happen. It's not clear. So as soon as, when the mass of the shell is big, so here, clearly the semiclassical approximation holds, so these shells surely bounce in this fashion, but here near the center, something different might happen. So those are still toy models. So yeah, some singularities may appear here and there, but generally speaking, you get a bounce at the center of the star. So that's all we know as far as I understand. Okay.
Lucas, you well know Roger Penrose proved a very general theorem which shows that in a very general situation, the collapse of matter leads to creation of singularity. Which of the assumptions of the Penrose theorem is violated in your case?
Okay, that's a good question. I don't know exactly, but that's a good question. We should check, surely. Yeah, I don't know. Let's check. No, thank you for the question. Yes. Okay, sorry, I
think that actually the equations are not really satisfied because it's quantum gravity.
The equation of, I mean, the classical equation of motion clearly are not satisfied.
And then there is energy conditions.
Probably so, yeah. I mean, the energy condition, if you're far from the Planckian scale, maybe they still hold. But near the Planckian scale, surely they're, I mean, we expect it to be violated. So at least that one is, yeah, I guess it's violated. But maybe something else too, I don't know. But yeah, this is beyond classical GR, so we don't get the...
Yeah, that would be my bet. That's the energy condition. Wow. Wow. Yeah.
Okay.
Not unless
Don't turn it on. Off, yes.